The moment an operator strikes an arc against a steel plate, they are initiating a highly localized physics laboratory. In a fraction of a second, the process forces metal to cycle through all four observable states of matter. The system begins in the solid state. You have the cold steel of the base plate and the metallic core wire of the electrode, both sitting at ambient temperature. As thermal energy transfers into the system, the steel breaches its melting point, transitioning into the liquid state. This forms the active weld puddle on the plate, while molten droplets of the core wire detach and transfer across the gap. Simultaneously, the chemical coating on the outside of the electrode vaporizes. This rapid expansion creates the gas state, a dense shield that physically pushes atmospheric oxygen and nitrogen away from the vulnerable liquid metal. This cross-section illustrates an active weld puddle. Bridging the gap between the solid wire and liquid puddle is the fourth state of matter, plasma. When electrical current passes through the shielding gas, it excites the atoms, tearing electrons from their nuclei. This creates a plasma column approaching 10,000 degrees Fahrenheit. Despite these temperatures and pressures occurring at the microscopic level, this entire environment is guided entirely by the micro-movements of a human hand. Mastering shielded metal arc welding requires looking past the blinding glare of the light to actively manipulate these four physical states in real time. The delivery mechanism for this complex plasma and gas system is the coated welding electrode. For decades, metallurgists have been analyzing and refining these rod coatings to meet highly specific industrial and structural demands. The metallic core wire provides the physical filler material. The chemical coating on the outside dictates the physics of the arc. These specific chemical formulations are engineered to fabricate the massive, high-stress structural steel frameworks that support modern infrastructure. An electrode is a self-contained, consumable chemical engine designed to dictate the metallurgical structure and mechanical properties of the finished weld. Functionally, the electrical arc serves two purposes. It is the primary heat source, melting the steel, and it is the physical pathway for the molten metal to transfer across the joint. Welders manipulate this pathway through arc length modulation, making deliberate millimeter-scale adjustments to the physical gap between the tip of the rod and the base metal. Pulling the electrode away from the plate increases electrical resistance, forcing voltage to rise. This high voltage spreads thermal energy widely, failing to reach the joint's bottom edges. Conversely, pushing the electrode closer lowers resistance and voltage. This concentrates energy into a tight column, allowing deep root fusion. Through subtle adjustments in wrist angle and height, the operator directly controls the voltage, dictating the exact thermodynamic footprint of the weld. Alongside arc length, the operator must manage polarity, the specific direction of the direct current flowing between the electrode and the workpiece. In direct current electrode positive, or DCEP, the positive terminal generates 2/3 of the total heat. DCEP drives this thermal energy downward into the base metal for deep penetration. Reversing the flow to DCEN concentrates that heat onto the rod itself, resulting in faster deposition but shallower penetration. An operator can also select alternating current, which switches the flow direction 60 times a second to balance the heat distribution and prevent magnetic arc blow in tight corners. Selecting a polarity dictates where the thermal payload is placed. It is a calculated decision based entirely on the thickness and geometry of the joint. The physics of the arc are heavily influenced by the flux chemistry. The active weld pool is a volatile mixture of melted base metal, core wire, and vaporized flux compounds. On the left, a 60-10 cellulosic rod combusts rapidly, releasing high hydrogen gas. This increases resistance and voltage, producing an aggressive plasma stream that blasts through rust. On the right, a 70-18 low hydrogen rod produces a calm carbon dioxide shield, using chemical scavengers to deposit tough, crack-resistant steel. This clean chemistry is why low hydrogen electrodes are mandated for dynamic load applications, from bridges to heavy pressure vessels. Choosing between a 60-10 and a 70-18 rod dictates the chemical makeup of the plasma, directly altering the physical behavior of the metal transfer. As thermal energy rapidly transfers into the cold base metal, the liquid weld pool freezes from the outside in, stacking chaotic atoms into structured crystal lattices. Fast cooling generates fine, tightly interlocking grains for high strength. Excessively slow cooling yields coarse, blocky grains that are structurally weaker. If the cooling cycle and flux are mismanaged, defects occur. A deep, aggressive 60-10 pass leaves narrow trenches. If the next pass bridges over those trenches without melting them out, it traps lines of solid slag inside the steel, a physical defect known as wagon tracks. An even more dangerous chemical threat occurs if a 70-18 rod absorbs ambient moisture from the air. The extreme heat of the arc breaks that water down, releasing monatomic hydrogen directly into the plasma. This hydrogen readily diffuses into the liquid metal. If the weld cools too rapidly, the steel transforms into a hard, brittle microstructure called martensite, permanently trapping those wandering hydrogen atoms inside the rigid crystal lattice. Internal pressure builds until the tensile limit is breached, and the steel violently tears itself apart from the inside. This is hydrogen-induced cracking. A weld can look visually flawless on the surface, while hiding fatal atomic-level fractures caused by a mismanaged thermal cycle or contaminated flux. We see the culmination of these physics in the exact moment the welder breaks the arc, removing the electrical heat source. Without the steady deposition of new filler metal to feed the puddle, the liquid steel is subjected to intense surface tension, pulling the cooling edges outward and leaving a dimpled crater. This thermal heat map shows a top-down view of the crater. Because edges cool first, the dead center is the last microscopic volume to freeze. As surrounding metal solidifies, remaining chemical impurities, dissolved gases, and shrinkage stresses are pushed inward, concentrating into this final vulnerable zone. Understanding this cooling dynamic demonstrates why rigorous mechanical grinding of stops and starts and proper step-back restart techniques are mandatory for any code quality procedure. Heavy structural and pipeline welding is an application of thermodynamics and metallurgy, executed under extreme field conditions. In upcoming modules, we will break down the pushing forces of the arc, the pinch effect of metal transfer, and advanced AC and DC applications. The integrity of the joint depends on an operator's ability to manage these specific interactions between plasma physics, volatile flux chemistry, and thermal gradients.